Alright, I'm Taylor Ullman,
I'm Laura Tyson.
Megan Trumpa.
and we did the mathematics in Aquariums.
So we chose this topic because we were kind of just trying to think of like something that would be a good idea and had like different mathematic concepts that we could talk about. And we Googled it and like went down lists, and aquariums just kind of sounded interesting, and it was something that really none of us knew very much about. So we thought it'd be a good learning opportunity.
Alright, to start off with our history, we're going to go right away with Robert Warrington. Most pet fish were kept by primitive means until 1850. Robert Warrington started a theory that kept plants, sand snails, and fish in an aquarium. This way it was a self-sustaining fish tank that the plants would supply the oxygen that the fish needed, and the snails would eat the decaying plants and lay eggs, and the fish would feed off the snails' eggs. So just constant life cycle that he created so that you could keep fish for a longer time. And then here's just a picture of a 1800s style fish tank. Nothing too fancy, as you can tell.
The first recording of fish being kept as pets was in China during the Song Dynasty in 960. Goldfish were primarily controlled by the Chinese until 1616 when they were found in Japan. And then after making its way through the world, goldfish arrived in the United States in 1850, and in 1888 the first breeder opened up in Maryland and started selling them as pets. In 1908, a mechanical air pump was invented, which was powered by running water to filter the water in the tanks. And then aquarium fish were fed a diet of live food until 1952, when Dr. Banch created flake fish food. In the 1960s and 70s, improvement to filtration and skinning systems increased the quality of fish life. In 1996, aquarium keeping was the second most popular hobby in the United States. 3 years later, 9.6 million households owned an aquarium, and by 2006, over 150 million fish were kept in aquariums in the U.S.
Alright, so then we just have a picture of a more recent tank, saltwater. Okay, and then there's two different types of fish tanks. There's freshwater and saltwater, just mainly the type of animals that are able to live in each different habitat. Saltwater has similar characteristics to freshwater, with many different chemical differences in the salinity of the water. Saltwater has different freezing points and boiling points as well, and I'm not sure how to pronounce this. The ear Elaine fish are species that can live in both freshwater and saltwater. And so right here I got a picture of a saltwater and a freshwater aquarium. The main differences between the aquariums is just, like I said, the type of fish that can live in it, and also the type of coral that's able to survive in different habitats. Like in freshwater, it's mostly plants like your trees and roots and stuff like that, and then in saltwater you see more of those tropical corals.
Galileo, in his experience with the physics of motion, was the first to use distance related to time, which is velocity. Over a 20-year period, Galileo experimented and questioned the theories of motion. He observed the motions of objects rolling down multiple inclined surfaces and measured the distance a ball rolled in a given amount of time. And velocity is distance over time. And this is how one would find the velocity. You would take the final position minus the initial position to find the total distance traveled, then divide it by the final time minus the initial time. So, and then the average speed of a goldfish is 100 feet per minute. So you would have So to put that into meters per second, you have 100 feet over 1 minute times 1 minute over 60 seconds times 1 meter over 3.2 feet. And then the feet cancel out, the minutes cancel out, and you've got 0.508 meters per second. Galileo noticed the objects don't continuously stay at the same speed. Objects speed up when going down steeper surfaces, and objects slow down when there's a lot of friction. Acceleration is the rate of change in speed of an object, and he discovered that the distance traveled by an object is proportional to the square of the time that it was in motion. Using these experiments is how Galileo developed the first correct concept of acceleration. Newton questioned why acceleration occurred, and by applying his second law of motion, he demonstrated what causes acceleration. Newton's second law of motion is the basic equation: force equals mass times acceleration, and an unbalanced force, push or pull, acts on an object to create acceleration. And then to find acceleration, it is the rate at which an object changes its velocity, so you take the final velocity subtracted, final velocity minus initial velocity over the final time minus the initial time. And then for the goldfish, the final velocity was 0.5 meters per second, and the initial velocity was 0. So you take 0.5 minus 0 over the final time minus the initial time, which was 4 minus 0. So you got 0.125 meters per second squared, which was the average acceleration of the goldfish.
Alright, so we'll go next to related rates. The history of related rates problems date back to at least 1836 when Reverend William Ritchie, professor of natural philosophy at London University, and J.J. Sylvester published Principles of the Differential and Integral Calculus. In their publishings, they found problems such as the one I have put there. This was actually one of their first ones in their publishings. The penny, if a half penny be placed on a hot shovel so as to expand uniformly at the rate, is its surface increasing when a diameter is passing the limit of 1 inch and 1/10, the diameter being supposed to increase uniformly at the rate of 0.01 of an inch per second. And then continued, Ritchie worked to simplify the presentation of calculus so that the subject would be more accessible to the ordinary non-university student. Drawing upon Newton, Ritchie took the change in magnitude over time as the fundamental explanatory concept from which he creates familiar examples illustrating the ideas of calculus. Okay, so then we did the application of related rates. I created just kind of an example question to do, and it says how fast does the water level drop in a rectangular tank with the base being a square with a width of 10 inches or length and width of 10 inches, and it drains at 20 inches cubed per minute. So then we kind of have to set up the equation or figure out what the values are. H is the height of the tank, L is the length, and W is the width. And then we have dV dt is the change in volume, and dH dt is the change in the water level. Alright, so over on the left, we start off with the volume with is length times width times height. And since the bottom is a square of 10 inches, length and width are both 10 inches. We do not know the height, but we know the change in volume is 20 inches cubed per minute. And we're trying to find dH dt, which is the change in height. So here we started off and we plugged in 10 to L and W, and we got 100 H. And then what you do from there is take the derivative. So dV dt equals 100 dH dt. And then, so dV dt equals 20. So we plug that into there and divided 100 by it. And we figured that the rate at which the water level is dropping is 0.2 inches per minute. Alright, so next we'll go to exponential growth and decay. Reverend Thomas Malthus studied population control and warned that the population growth would exceed food supply. Applied the exponent function to growth constraints. When developing his method, his main focus was on the relationships between population growth, wages, and inflation. He discovered how this was an important theory to avoid societal human disaster. And so now we go to the application of exponential growth. And so the equation for it is y equals ce to the kt power. And y is the amount of material after a certain amount of time. And then c is our initial value and constant. And k is a proportional constant. And k has to be greater than 0 for results in growth. And then t will be our time. Okay, so how I set this up is we, at the start of time, we had 2 fish, and then after 30 days, we had 4 fish, and we're trying to figure out how many fish we have after 60 days. So to set that up, so our initial amount is 2, so we plug 2 in for C, and then the amount that we get after time is 4, so we put that in for Y, and amount of time in days was 30. So what we did from there is we divided 2 out to get 2 equals e to the k times 30, and then we use natural log to bring down the 30k power, and the natural log of e is going to be 1, so there is no longer a log on this side. So from there we divided 30 from the ln of 2, and our k got to be 0.023. So then from there we still have to figure out how many fish are there after 60 days. So now we go and plug it into this equation. So we're trying to figure out the amount of fish, so we keep y as a variable, and we have it equal to 2e to the 0.23 power, and then our new time we're trying to figure out is after 60 days. And we solve that, and you would have 7, well, if you are not counting parts of fish, we have for sure 7 fish at the end of 60 days.
Some fish eat their young.
So another math concept we did was like the volume of the tank, and Archimedes was who discovered volume, and his first like experiment wasn't on purpose. He was like in a bathtub, you're going to go take a bath, and he noticed how like the lower he sat down, like the more water like rose up, and so he figured that like the amount of water that was displaced was equal to his body volume, and so he basically like ran out of that room and like went to go do other experiments to continue to find formulas and the volume of other objects. So for the application of volume for our aquarium, like the volume is just like the amount of space that like an object takes up. So if we had like a rectangular aquarium, it would be length times width times height, which is find the total amount of space that it takes up. So here we have this one, just an example that has a length of 10 inches, a width of 10 inches, and 12 inches as its height. So when you multiply them together, that is equal to 1,200 inches cubed. And then kind of building off of that, you can also find the surface area, which is just like the total amount of area that like the exposed part of the tank takes up. So like if you have multiple different sides of the tank, you would like take the areas of them, which would just be like the length times the width, and then you would add them together. So for the history of surface area, kind of going off of Archimedes' like formulas that he developed for volume, Henry Lebesgue and Hermann Minkowski at the beginning of the 20th century began to study these formulas, and also previously to that Einstein created some formulas, but was studying that, but he wasn't able to prove that they were actually accurate. So after Henry and Hermann tested these theories, they proved that they were accurate, and they developed the geometric measure theory, which just is basically studies multiple theories of surface areas to like find the surface area for irregular shapes. So if you have like a tank here, like I said, you're just going to like find the area of each side, and this one has 5 since it's a tank. It doesn't have a top to it, as if like it didn't have a cover on it. So you'd find the areas of each side and then add them together. So you have the bottom square, which is just like the base underneath, which is 10 by 10. So you multiply that together, and then all the other sides are 10 by 12. So you can just do 10 times 12, and then multiply that by 4, and then you'll get a total of 580 inches squared for the surface area of a tank of that size. That's just kind of like basic how you find the surface area of just a regular rectangular tank. And then those are all of our applications.